Record. Okay, so yes, chapter 20. So we are now on chapter 20. I have no idea what lecture number this is.
17.
17, 18, 19, I don't know, something like that.
Or 18.
You should just label your YouTube videos the chapter.
Pause this for a second. There's always markers in the next room. So, okay, so chapter 20. Inference about a population mean. So last time we did chapter 19. And if you recall about chapter 19, it was the sampling distribution for a mean. So let's recall that. So recall from chapter 19 that if X is normal with a mean mu and a standard deviation sigma, then can someone remind me what X bar is? What is the distribution for X bar if X is itself normal? Yes? It's also normal.
Also normal, and then the
Mu is the same.
and then it's over the square root of n.
Excellent. The standard deviation shrinks, gets smaller by a factor of 1 over the square root of n. What if X is not normal? What if X is just an unknown distribution whose mean is mu and whose standard deviation is sigma? Then what is X bar? Well, the same thing under a condition. No, the successes and failures condition was for proportions. Now we're talking about means. It's a different condition. If n, the sample size, is large enough, and as a rule of thumb, we say greater than or equal to 30. And what theorem tells us that we can do this? What's the name of the theorem that says that no matter the underlying distribution, X bar has this property? The central limit theorem. And in previous semesters, not every final question or even every exam question is mathematical in nature. Some of them are conceptual. And you might see a question like, which theorem is it that lets us do this? And it could be, oh, that's the law of large numbers, or that's the central limit theorem, or that's this, or that's that. So you should certainly know which theorems allow different things. So that was chapter 19, the sampling distribution of the mean. And now we're going to chapter 20, which is now we want to make inferences about a mean. In other words, just like we did hypothesis testing for proportions, and we did confidence intervals for proportions, we would also like to do the same thing. Yeah, for means. So what is going on? Hey, he wants your attention. Someone over there. Okay, good talk. So chapter 20. We want to do hypothesis testing and we want to do confidence intervals for a mean. I understand.
Wait. Oh, sick.
What? Oh, too bad. So chapter 20. Inference about a mean. Now, just like proportions, when it comes to, yes?
The mean of population is the way you said population.
Well, you don't have to make an inference about a sample mean because you have it in front of you.
Okay.
The only thing you'd want to make an inference about is the population mean.
But what do we write?
You can write that. So, inference about a population mean. You take a sample. I'm curious what the average height of every CSUN student is, so I take a sample and I get a value. And I'm curious, how close is that value to the true value that I will never know? Just like in the previous chapters for proportions. What's the true proportion? I don't know. I'll take a sample. Oh, what's so funny? You chilling? Okay. So in previous chapters, I wasn't sure what the true proportion was. So I took a sample and I said, oh, here's my sample proportion. So I'll make a confidence interval about that sample proportion. And I'll have a certain confidence that I've caught the true proportion. Now we'll do the same thing for means. I'll make a confidence interval about my mean, and I'll have a certain confidence that I caught it. Or I'll do a hypothesis test. I'll come in and say, well, you know, Subway, you claim that your foot-long sandwiches are a foot long, and I've had a few, and I always bring a ruler with me wherever I go because, you know, that's what normal people do. And I measured the length of the sandwich every time I've gone, and I'm sorry to say, but they're only about 11 inches. So I think that you're lying to us, and therefore I'm going to sue you. This is a true thing. I read in the news like a couple of years ago. I don't know if you remember this story. Someone actually sued Subway because they took a sample and they found that in their sample, their sandwiches were less than 12 inches. So what they did is they did a statistical test. What's so funny? I don't understand. Why is everyone laughing today?
It's nice news, Brad.
Okay. I don't understand what's happening. Anyways, there's two basic categories of inferences about means. And those two categories are either we know sigma or we don't know sigma. And depending on whether or not we know sigma or we don't know sigma, actually determines which of two different tests or confidence interval approaches that we're going to use. And if you actually look at your calculator and you look at the tests that it has, the tests on your calculator, you'll notice that there's two tests that are appropriate for mean. So ignore the proportions, ignore the two sample tests because we're only getting one sample in this chapter, and tell me what two tests are written on or are listed on your calculator if we ignore the proportion tests and we ignore the two sample tests. You should be two of them. Z and T. The Z test and the T test. If we know sigma, we use the Z test. If we do not know sigma, we use the T test. The T distribution is like a normal distribution. It's like a Z, the normal distribution. It's just a little bit wider. Why did we use the T instead of the Z? The reason essentially is because since we don't know sigma, there's an added layer of uncertainty in our work. And that added layer of uncertainty creates a slightly wider confidence interval. And if you're trying to catch sigma, not sigma, sorry, if you're trying to catch the mean, you want as small of an interval as possible, right? What's good as they can do to say, yeah, I took my sample, the average height of a CSUN student is somewhere between 5'2" and 6'3". It might be a true statement, but Is it helpful to know that? Not really. It's too wide of an interval. Not knowing sigma gives us a wider interval because we have to compensate for the little bit extra that we don't know. The t-test does that for us. To use the t-test, we had to know how many degrees of freedom there are. If you actually look at the t-test, if you load it up on your calculator, if you go to the t-test, what information does it ask for? What are the inputs that you need in order to do the t-test on your calculator? I can't hear everyone at once. Stats.
And then it's
Mu zero, you have to know, well, you have to know your assumed value, just like we had p zero for your assumed proportion. You have to know your mu zero, your assumed mu, your assumed mean. What else? X bar is your sample mean. Just like your proportions, we had our x and n to give us our sample proportion. We have to know our sample mean. What else? S of x is your sample standard deviation. We don't know sigma, right? Well, if we don't know the population standard deviation, what's the best thing we can use to approximate it? The sample standard deviation, which is why one of the inputs is S sub x, the sample standard deviation. What else is there? N, which is your sample size. So what do we need? We need mu naught, we need x bar, we need Sx, we need N. What else is there? That's it. So this degrees of freedom thing, it better be encapsulated somewhere in these four. And in fact, it is. The degrees of freedom is n minus 1. Now, your calculator does not require you to give it the degrees of freedom because your calculator, you'll give it n, the sample size. And your calculator knows that the degrees of freedom is n minus 1. So this piece of information here, not really necessary if you're going to do it by calculator. However, if you load up a t-table, which we're not going to need, but if you load up a t-table, you should see degrees of freedom listed as something that you need to input. Okay, we're not going to, maybe we'll do it if we have time, but since your calculator does so much for us, we're not going to worry about it too much. On the other hand, if I do a z-test, what do I need for the z-test? Go to your calculator, load up z-test. What are the inputs that I need for the z-test? Still stats. Okay, data means you're actually putting in your actual data itself. Okay, in which case it computes everything for you.
And you have to say mu zero.
You still need mu zero, your assumed value.
Then you have your sigma.
You still, now you have sigma because we know it.
And you have your
We have our x bar, which is our assumed, our sample mean, and what else? And we have n. So in each case, you need 4 pieces of information. You need the sample size, which is where your degrees of freedom comes from. You need your mu naught, your assumed value for the mean. You need your x bar, your actual sample mean, and you need your deviation, whether it's the true value or your sample value when you don't know your true value. Yes, question. I answered the question.
Yeah.
Okay. In both cases, what is that single number at the end of the problem that we're trying to get? That single number which answers all of our questions. Your p-value. At the end of the day, the goal is still to get your p-value. And what do you do with the p-value?
Determine whether it's significant or not.
Determine whether what is significant. The word it, I don't know what the word it means. No, see, that's the thing. The word it is a catchphrase for something, which is why I hate it. You got to say specifically, what is the it? Yes. So what is what your sample means? I forgot even what he said.
Like you're trying to find the significance of it.
You're trying to find, not exactly. You're not trying to find the significance of something. You're trying to determine whether your result is significant or not. The result is significant. What p-values tell you that your result is significant?
If it's less than 5%.
If it's less than 5% or whatever the value is for that problem, if they give me a different value. Usually it's 5%, but if they say tested at the 1% level, then that's your cutoff. It's got to be less than 1%. Yes.
So if it's greater than it's fine.
Not it's fine. There's no it's fine. because remember, it's like, because in statistics, we don't have a vested interest in the answer. We don't care whether we reject the null hypothesis or not. From an emotional standpoint, if I'm doing Subway, I want to reject the null hypothesis. They're claiming it's equal to 12. I say, no, it's less than 12. I would love it to be less than 12 so I can sue them, make a lot of money. But from a statistical standpoint, the math is the math. Either the result is not significant and I do not reject the null hypothesis, or the result is significant and I do reject the null hypothesis in favor of the alternative. Does that make sense?
Yeah.
So at the end of the day, the p-value is all you need. The one number. Is it small? The p-value is low? The null must go. If the p-value is high, let it fly. I don't really like that one so much. I like the other one, but anyways, it is what it is. Okay. Now, this is for hypothesis testing. But hypothesis testing is only half of what we do. What's the other half? Confidence intervals. So let's go back to our calculator and let's scroll down, get past the tests to the interval portion of the problem of the calculator. And which two different types of confidence intervals are we going to use based upon the calculator? The what? The Z interval or the T interval. When will we use the Z interval?
When you know the standard deviation.
When you know sigma. When we use the T interval? When you don't. If you click on those buttons, Z and T, what do they ask for? What must you provide in order to use the Z and T intervals? Well, I can tell you right now, you're not going to be providing those guys. Because what's the major difference between hypothesis testing and confidence intervals? For hypothesis testing, you're coming in and you're saying, oh, you think this is what it's equal to? Well, let's test that. You think it's equal to this? I'll test it. You think it's equal to this? I'll test it. For confidence intervals, you don't have any idea what it is. So you're not testing anything, so that's going to be gone. But the other stuff is probably going to be there. So let's do the Z first. The Z interval. What must you use? What do you have to input in your calculator to do a Z interval? Sigma, X bar, and N. And probably the confidence level as well, right? So now you need it for a Z interval. Instead of mu naught, now you're going to have to put in your, not your Z star, but your confidence level. The Z interval. And what about for the T interval? What do you need for that one? Sorry? Same three things, but now in this case, instead of mu naught, it's again going to be the confidence level. So one of the reasons I say that the chapters at the end of the course are relatively straightforward is because you're not really conceptually learning anything different. The confidence interval stuff and the hypothesis test stuff that we're doing now is, from a calculator perspective, almost exactly the same as what we've done before. You have to get different values when you plug them in and you get your answer. Your conclusions, everything exactly the same. Yes.
What is X bar represented?
X bar is your sample mean.
Okay.
See, for proportions, we don't care about the sample mean. There is no sample mean. We care about the sample proportion. But now we're doing it about means, right? We've done one proportion, confidence intervals and hypothesis tests. We've done two proportions, confidence intervals and hypothesis tests. Now we're doing a sample mean, a single population mean, confidence interval and hypothesis tests. Anyone want to take a guess as to what the next chapter is going to be about? Huh? Two means. Just like we had, no, it's not hard. Back to the calculator. Scroll down to your calculator. What do you think we're going to be doing when we get to the next chapter? Not prop, that's proportions. Two sample Z or two sample T. And again, it's just, here's all your data, or here's all your numbers, plug it into the calculator, out pops your p-value, you make your conclusion. Does that make sense in general? So let's go ahead. Question? Yeah.
What is SX for two don't know sigma?
SX is your sample standard deviation. Okay.
What do you mean when you say p-value is less than 5%? I
It is, and is it less than 0.05? A p-value is a probability. It's a less than 0.05. A p-value at the end of the day is a probability. It's how likely it is that you're getting a certain outcome. So let's focus first. Let's go in the order of the stuff in the book. And the first section that they do, if I read this correctly, is it looks like, well, before we get to the actual formulas, let's do the following. The conditions needed to form an inference for a population mean. Okay, if you recall, for proportions, we had certain conditions, right? It had to have 10 successes and 10 failures, right? It had to come from an SRS, right? We had various conditions, correct? So here also we have conditions. Now, in this course, you're going to assume that these conditions are always met, because if they're not, you can't do any math. They're not going to give you a problem where you can't do any math. That's silly. But if you're actually try to use statistics out there in the world for whatever reason, you want to make sure that the conditions are actually met before you use any of these. So number one, condition number one, the data comes from an SRS. Okay, it has to be a simple random sample for us to do anything. The data must come from an SRS. Two, the underlying distribution. The underlying distribution must be normal. Must come from a normal distribution. Or approximately normal.
When you say approximately normal, does that mean you have to go through the circumstances, the samples size are greater than 30?
Well, not exactly. I'm going to give you numbers in a second for it. But approximately normal basically means that it's single peaked and it's symmetric. So the t distribution, for example, is not normal, but it kind of looks the same. So if this is a normal distribution, a t distribution will be a little wider and a little shallower. It's not technically normal, but it still is symmetric with a single peak in the center. So that's what we mean by approximately normal. Again, in the context of this course, you don't really need to worry about it too much. Condition number three. If the distribution is moderately skewed, so it starts to deviate from normality a little bit. If it's moderately skewed with no outliers, and the sample size should be greater than or equal to 15. As we saw on that applet, by the time n is greater than or equal to 15, if the distribution starts in the normal vicinity anyway, it's close enough by the time n is 15 to not have to worry about it. Okay, so if the distribution is moderately skewed with no outliers, n must be greater than or equal to 15. If
If it's normal, does that rule still apply?
No, if it's normal, if it's actually normal, then n could be 1 and you're good. Sample size of 1, you're fine. If it's moderately skewed, so it's not normal, of course, if it's moderately skewed with no outliers, n must be greater than or equal to 15. If it's strongly skewed, if the distribution is strongly skewed, with no outliers, then n must be greater than or equal to 40. So approximately normal. Moderately skewed and greater than or equal to 15, strongly skewed and greater than or equal to 40. Yes.
If there are outliers, can we just not use the data at all?
If there's outliers, you shouldn't use anything from this section.
But we're probably not gonna get problems.
No, because you can't do anything. I mean, unless the purpose of the problem is for you to recognize that. And one of the options, let's say, have multiple choices, sorry, can't do anything. Maybe, but in general, from a mathematical standpoint, you're not going to be given any problem. You can't do the math. Of course, in the case of the proportions, remember, we had that first condition, 10 successes and failures. And if it failed that, we had a second condition, and then we could move to the +4 confidence interval and hypothesis test. So if you can't use one, you might use something else. For this one, we only have one. There's no backup plan. Okay, yes.
So what do you mean by like, I don't understand the distribution.
If it's normal,
Okay.
great, you can use everything we're gonna do here.
Okay.
If it's approximately normal, you can. But wait a second, approximately normal, how approximate? Well, if it's moderately skewed, then make sure n is greater than or equal to 15.
Okay.
If it's strongly skewed,
Then it has to be
then it's got
greater.
to make sure it's greater than or equal to 40.
Okay.
Okay. So now that we have those conditions down, can I erase?
Yeah, so it's basically just like this one, you can raise, but it's basically just like the graph, like on the right side, that's strongly. And if it's like.
Yeah, what you said. Right. Again, you're not going to be given anything which mathematically you won't be able to work. So now that we have that, let's start with the first thing the book does, the one sample t interval. When do we use t again? If we don't know sigma. So what is the one sample t interval? Well, every interval, whether it was the case of proportions or means, every interval starts with your actual value that you got from your data. Your best guess. The one number, that if you had to pick one number, and this would be the number to pick. What is the one best number to pick if I just took some data trying to calculate a t interval for a mean? What is my best guess for the true value of the mean?
0.
No, that's 0. My sample mean. The sample mean, yeah. I wonder what the average height of every American is. My best guess is 0. No, my best guess is my sample mean. Nothing beats that as an initial guess. But what do? We take that value and we form a confidence interval by adding or subtracting a given amount. Now, in the case of the population, the proportion confidence intervals, what did I add and subtract? Anyone remember what it was? It was p hat plus or minus, not z score, but rather z star. However, z is wonderful when you know sigma. I don't know sigma here. So here I'm going to use t star. Times the standard, the square root of what? Well, this is proportions you're doing now, right? Proportions with the square root of what? P hat, 1 minus p hat over n. Why did we use, in the case of proportions, why did we use this as a thing that I added and subtracted? Anyone remember why I used that? because this was the standard deviation of my sample distribution. Well, what is the standard deviation of my sample distribution now? I gave it to you. We talked about it a few times already. What is the, huh? Come on, guess. What is it? No, come on. Well, X bar is your sample distribution. So what is the, not exactly. Sigma was the sample deviation of X of your population. But we're looking for the sample distribution, for the X bar distribution. What was our sigma for the sample distribution? Remember the central limit theorem? If X is n of mu sigma, then X bar is n of mu sigma over the square root of n. But wait, I don't know sigma. I can't use sigma over the square root of n because I don't know sigma. That's why I'm using t. So what's the best thing I can do to replace sigma with? S of x. So my confidence interval for the t is X bar, my sample mean, plus or minus t star, not z star, but t star, S of x over the square root of x. Yes? How do you find t star? It's a great question. If only we had a way of finding t star much like we did with z star. How do we find z star again? Someone remind me. Inverse norm. We use the inverse norm because it was a z distribution. Is there an inverse t in your calculator? Can we check? Is it there? That's crazy. So yes, to find t star, we use the inverse t. It's right below the inverse z, right below the inverse norm. Go to second vars distribution, and you should find the inverse t. So for example, what was the z star? Someone remind me. What was z star for 90%? 1.645. Because I told you to remember that. What is the t star for 90%? You gotta find a DF. You gotta find a DF. The one thing it asks for in inverse t besides 90% is the DF. What do you think DF stands for? Degrees of freedom. What's the formula for degrees of freedom? N minus 1, sample size minus 1. Well, we don't have a sample size because this is abstract, but let's pick one. Why don't we do a couple? Let's do, fine, okay, 3. So let's do an n equals 3, 90% t star, and tell me what we get.
So we do everything to the left, right?
No, you shouldn't have that option for t star. Do you have that option? No, you shouldn't have that option. It should automatically give you the center. I think. I forgot my calculator at home, so. That's an older version. You're not getting extra credit, Jesus Christ. Well, that's the older version. I don't know how to use that one. Yeah, okay. Hold on. I gotta do 95%, 90%. And if I do 95%. Yeah, it's to the left. Okay, yeah, inverse t goes to the left. So if I want to find 90% t star, you put 95%, you put 0.95. Because remember, 90% in the middle, because this is a confidence interval, 90% in the middle is 95% to the left of the point that I'm looking for. Right? Remember, T star is the end of the 90% section, the middle of the 90%, which is 95% to the left. So when you do n equals 3, what do you get for your T star?
You put DF is 2, right?
DF is 2. If n is 3, DF is 2. What do you get? I can't hear what?
2.92.
2.92,
Why is DF two?
because DF is n minus 1. If n equals 3, DF is 2. How does 2.92 compare to 1.645?
More.
It's bigger, which means that your plus or minus part, you'll be adding and subtracting a bigger number, correct? It's going to be wider. What happens when n goes up to, let's say, 30? Let's calculate our 90% T star. Remember, if n equals 30, what's your DF? 29. What's our n equals 30 T star?
1.69.
Anyone but you. Huh? Okay, 1.69.
Come on, round it up.
And if you go n equals 100, what do we get when n equals 100? Which is 99 degrees of freedom.
1.66.
1.6 what?
6.
1.66. So what's happening as our sample size gets larger?
Getting smaller.
It's getting smaller and it's approaching what number?
1.645. 1.645.
It's approaching 1.645. 1.645,
So it's the same row as the other one where the larger your sample size is, the closer.
the larger your sample size, the less your uncertainty matters. Because remember, why are we using T star instead of Z star is because we don't know sigma. So we're compensating by making it wider. But the bigger your sample size is, the less that matters. So as n gets extremely large, your T star value will approach your Z star value.
Is that always the rule?
Always the rule. Always the rule.
That you had 5%.
Huh?
That you had 5% area.
You always add half of what's left. So if I asked you for the 95% T star, how much would you add? You'd add 2.5%. If I asked you for 95, what's left? 5%. Half of that, 2.5%, 97.5. You always add half of what's left. Because remember, if this is what you have in the middle, then the wings, you want one wing, it's half of what's left. That's always half of what's left. Now, in tables, if you use a table, first of all, look how many decimal places your calculator gives you. It gives you like 8 decimal places. A table is not going to do that. A table is going to round. But a table also doesn't have every n from 1 to infinity. It goes like from n equals 2 up until like 40. And then it goes 50, 60, 70, 80, 90, 100, and then 1,000. And then I think that's it. If you load it up right now on your calculator or whatever internet connection you have. Normally, if I was teaching on Zoom, I would do it myself, but I can't do that right now. I'll go ahead and load up a T star table.
Where did you go to do that?
Google T star table.
Oh.
Just do a Google search right now or a T table. Just do a Google search right now for a T table. Okay, everyone should do this because, or if you don't do it yourself, look at someone next to you who is. Load up on the internet via the phone or whatever, a T table. Google T table and go to the images and pick one. Shouldn't matter which one you use. They should all be pretty much the same. Well, do you have the table? What do you see on the left? The left column, what do you see? DF, degrees of freedom. Look at the values for DF from top to bottom. It goes from 1 up to what? Up until 30. And then it goes by 10s up until, well, it goes by 10s up until 100. And then what's next? 1,000. Then what's next? Huh? What's the line after that? Does it have any line after that? It says Z, because once you get large enough, you're essentially Z.
So 1,000 is what we.
Well, not 1,000. Technically, if you go far enough along decimal wise, even a million's not going to be there, but you're close enough. Now, if you were using the table, which doesn't give you every n, and you had a sample size, let's say 45. If I had a sample size of 45 on the table, which is how many degrees of freedom? 44, but there's no row for 44. So I got to either go to the row above or the row beneath. Which one do I do? Why? Why?
44, 45, you go up.
No. Yes.
You want to make sure that it's as accurate as possible. So you go lower, because if you go higher, you're not sure.
Just the opposite. You want to be as accurate as possible. If you go lower, you're erring on the side of a smaller confidence interval, which you can't justify. Right? The smaller you go on the table, the smaller your T-star values get, correct? So your confidence interval will be smaller. But you can't justify having a confidence interval of that width when n is really 45. But you can always go to a higher value on the table, which is a wider confidence interval. And okay, so it's wider, but at least you're not justifying anything better. Okay, so you'll always go up. If you're between two, you go up, yes? Clairvoyant. If you're between two, you go up. With a calculator, you don't got to worry about that, because your calculator will give you the correct value no matter what. Your calculator is programmed to do everything. But if you don't have a calculator, you go to the table. Now you had a photocopy of one. Where did you get that from?
I have like all the tables.
You just have all the tables. It's wonderful. In fact, may I borrow for a second? So this is chi-squared. It's not t.
Oh, this side.
This is correlation. Unbelievable. You know, never mind. So the point is, on the table, forget it. This guy's here. On the table, on the left of the table, you will have your degrees of freedom. On the top of the table, what do you have? The percentages. 95%, 90%, right? 95%, 90%, and so you have the percentages. You go to the square or to the cell, that's the intersection between the correct row and the correct column. So let's do that. Let's go to n equals 30, which is degrees of freedom 29. Go 90%. Actually, if it's to the left, 95%. And let's find 1.69 as the value. Make sure you can do that on the table. Degrees of freedom 29. Area in between 90% to the left 95%. Different tables do it different ways. So for the table that you're looking at, make sure that you know which one they're using. Are they using area to the left, in which case we would use 95%? Or are they using area in the middle, in which case we use 90%? Andrea, which one are they using for yours? Can you tell?
To the right.
To the right. Well, if it's to the right, then we want 5%. Agreed? If it's to the right, then we're going to want the 5% column. And does it give 1.69?
Yes.
So make sure whichever table you use, you know which area they're asking for. There usually be a picture on top. Yes.
Are we gonna have it sit with the test?
No,
Or is
yeah,
the
calculator.
calculator's on
In your case, you'll notice that it is a shading on the sides, correct?
Right.
So if we want 90%, 10% value, so we're doing 10%. That you can have in here. So,
No, 1.6 hours on the night.
oh, wasn't 100%. Okay, so I guess they want the early note. 29. Yeah, like that. But yeah, I mean, back in the day, tables were really the only way to do these calculations. And you'll still have teachers here, even the math department, that are of the older persuasion, who still teach their entire course with tables. And the students never use the calculators. And I'm young, right? So on the other end of the spectrum, we have those who are embracing modern technology, like calculators that have been around for 30 years. And I try to do as much as I can with calculators. Does that make sense? So let's do an example. Oh, shit. Yes.
Okay, so if they're asking for the left side of the table, like 90, 95%,
If they want the left side of this point right here, this is what we're looking for, that point.
So then we're using 95.
So we would use 95%,
And then if you're asking for the middle, we're using
90%.
we
And if it's to the right, it would be 5%.
It's only 5%.
Well, 5% to the right of the point,
Okay.
right? And you have to look at whatever table you're dealing with to know what number to put in.
Got it.
Okay. So let's do an example.
When you said to the right, it was what percentage?
5%.
No, like on the.
5%.
So it'd be 95.
No, I said 5% to the right.
Just 5.
Well, if it's 95 to the left, it's got to be 5 to the right. It's got to add to 100, right? Okay, here's an example. 20.3. Good weather, good tips. Sorry. Good weather, good tips. It's a question mark. Does the expectation of good weather lead to more generous behavior? Psychologists study the size of the tip in a restaurant when a message indicating that the next day's weather.
Why did you look at me after that?
Stop me. So juvenile. Oh. Psychologists study the size of the tip in a restaurant. Guys, enough. What is wrong? Psychologists study the size of a gift in a restaurant when a message indicating that the next day's weather will be good was written on the bill. Here are the generous donations from 20 patrons measured in percent of the total bill. So this particular example actually gives me the percent values, which I could give you. And if I did give you them, 20.8, 18.7, and so on, if I did give you them, how would you incorporate that into your calculator work? Yes. So go to your, we're not going to do it this way because it's just a lot of time, but go to your T interval, your one sample T interval on your calculator, and it will give you two options. One of them is data and one of them is stats. It just says T interval. Okay, it doesn't say one sample, just T interval. Data and stat, right? If you click data, that means you have your actual data points. Where would I put those data points? In list one, right? I put my data points in list one, and I would have my calculator just read them. We're going to do it a different way. I'm going to give you for this example, I'm going to give you the data summary. So apparently X bar is 22.21 with a sample standard deviation of 1.963. And there were 20 donations. So N equals 20. The sample mean of those 20 was 22.21 with a standard deviation of 1.963. And the question now is to form a confidence interval based upon our data of the, at what confidence level? It says do it at 95%. So we want a 95% confidence interval for the true value of donations written when the weather is good. Yes. Did you do it already?
Yeah.
And what do you get?
For the lower one, 21.291.
21.291.
23.129.
23.129. And how do I interpret this answer? No, well, yes, but how do I interpret it? In the context of the problem, I had to write a sentence explaining my results.
That the amount per tip, and then that divides between 21.29 and 22.
Close, but you're making a statement of facts that I can't justify.
Okay, well, approximately.
I don't want the word approximately. I mean, I know what you're trying to say, but this is a key thing. The data supports the fact that the true value of a tip given when the weather is nice is between 21.291% of the bill and 23.129%. The data supports that. Is it definitely in there? I can't claim that. No, I don't know that it's within that range. I'm 95% confident that it's between that, in that range.
So the proper way to say it is the data support.
The data supports, or we have 95% confidence that the true value is somewhere in there. But to say the true value is in there, we can't. That's making a conclusion that we can't justify. Yes.
Where did you go in the calculator?
T interval?
Or just T interval?
Just T interval. Now, later, we're going to answer the question about whether good weather promotes better tips or not. And the only way we can do that is to compare the good weather tips to the bad weather tips. And that'll be a comparison of two different means, which is in the next chapter. Right now, we're focused on just what's the value for one? What's the value for this mean? Somewhere between those two numbers. Very, very straightforward using the T interval. Yes.
So we didn't use the C interval
Because we didn't know sigma.
Oh.
We had to use the sample standard deviation because I didn't know the actual standard deviation. If I did, I would have used sigma instead. And I would have used Z instead.
Is there a huge difference between the sample sigma and the population sigma?
I don't know, because I don't know the population sigma. Right? I have no idea. Now, are there tests, much like we're doing here, for sigma? Yes, there are, but we don't cover them in this class. We do the Z distribution, we do the T distribution, and at the end of the class in chapter 24, we're going to do the chi-square distribution. No, not really. What do we not use? We don't use the F distribution, which is used for sigma. And we don't use the T distribution for the context of like correlation and slopes of best fit lines. We don't do that in this course. When I tutor at other colleges around the area, Pierce, for example, when I've tutored at Pierce or at Moore Park, their statistics classes, they do a little more than we do. So different classes do different things, different levels do different things. So for the T interval, we saw it was X bar plus or minus T star S of X over the square root of N. What if we do know Z? What if we do know Z? Sorry, not Z, sigma. What if I did know sigma and I wanted to use the Z interval? What would my confidence interval formula be?
X bar,
X bar
T star,
plus or minus what?
T star.
Not T star. Why use T? Z star
Times the sum of sigma over T, square root of N.
Excellent. If I did know sigma, well, why would I use S? Why would I use the sample standard deviation if I actually know the true population deviation? Use that. And then why would I use T star if I know sigma? I wouldn't. I would use Z star. T star is the thing that we use when we don't know sigma, but if you know it, then use it. Z star will always be smaller than T star. Always. Even if N was like a gazillion and they're the same to the 100th decimal place, you go far enough along and T star will be a little bit bigger than Z star. Does that mean that a one sample T interval will always be larger than the corresponding one sample Z interval?
Yes.
And the answer is no. Because even though T star is bigger than Z star, that's not the only factor determining the interval. What else is there?
Sample size.
Sigma, no, the sample size appears in both in the same denominator, so that doesn't do anything. It's sigma versus SX. What if sigma is bigger than SX? That will make this interval a little bit wider. What if it's large enough in comparison that the overall interval here is bigger than the overall interval there? It can happen. Yes,
So Z star can be more than
Z star cannot be more than T star,
the whole thing.
but the whole thing could be bigger because of sigma being bigger than S of X.
Is that because sigma is the standard deviation of the population? So it's more accurate, so that number.
Well, sigma is certainly more accurate because we're assuming that we know the true value.
But
I mean, you can't get more accurate than the true value, right? It's when you don't have the true value that we approximate it with the sample. So now let's do the hypothesis tests for the mean. So hypothesis tests. In both cases, the null hypothesis will always be the same. In both cases, the null hypothesis will always be the same, which is what? No, 0.5 was proportions. And second, first of all, it wasn't always 0.5, like, oh, the coin's fair, 0.5. But it doesn't mean every proportion had an assumed value of 0.5. Second of all, we're dealing with means here. So what's the form of every null hypothesis for means? I'm sorry? It's what you assume mu to be. Mu is equal to a specific value. And what symbol do we use for that assumed specific value? Mu naught. Just like we had P, P hat, P twiddle, P naught, P star, P value. So mu is the true value. Mu naught is the assumed true value. And if you recall from the very beginning of today, when you go to your calculator and you do a Z and you do a hypothesis test for either Z or T, mu naught is one of the things that you have to provide. I go to Subway. They're like, you're claiming what? That the actual length is 12? So in their case, mu naught would be 12. Then I come along and I say, no, I have an alternative to that. And I have three possibilities for what the alternative is. What are the three generic possibilities for the alternative? What?
Greater, less than, or not?
Greater than, less than, or not equal to.
So mu naught will always be given to you.
It has to be. Or it can be inferred from the problem. You know, in reading the problem, either it's given to you or you can figure it out from the context. In the case of Subway, which of these three would be the alternative hypothesis that I would use? No, not equal to. Less than. I'm not going to say, no, you're lying. It's really 13 inches. Subway's like, okay, fine. I mean, they don't, no. When you come in and say, I'm sorry, you're claiming it's 12 inches long, but I don't think it is. Then you're saying, I think it's less than that. Right? Now, does Subway care if it's longer?
No.
Actually, they do. For a different reason. Why would Subway care if their actual lengths are 13? They're losing money. They're giving away free dough or whatever is needed. I don't know. Not free dough, but they're using too many resources that they don't have to. So on their end, they don't want it to be larger. They don't want it to be smaller. Larger for profits, smaller for getting sued. So we want to do a test. So what do? We take a sample. We take a sample, and somehow from that sample, we want to infer whether or not Subway's lying. Correct? So mu naught has to be given. Okay, we think it's 12. Then I take a sample of, let's say, 50 sandwiches. I know that's like lunch for me for a given day. So we take a sample of like 50 sandwiches. Okay, and then I have to compute what from that sample? Now what? P-value is at the end of the problem, obviously. But what do I have to compute to put into my test? Well, yes, maybe, unless I know sigma. But if it's not 12, why do I think it's not 12? Because my sample mean was less than 12, right? The average, the actual average of my sample, if it was 12.3, I'm not going to come to Subway and say, sorry, I really think it's less. The whole basis for my arguments, because of my sample, it was too small. Correct? So it's the X bar that matters. In the case of mu not equal to mu naught, where would my values have to land for me to reject the null hypothesis? Where would I say, huh? Well, where in general? I mean, just the right side? Just the right side? Just the right side?
No, I don't know.
Aggressive.
Which side?
You know what?
Either side. I'm claiming not equal to. If I'm claiming not equal to, then a big result or a small result will both be lending credence to my claim that it's not equal to, right? But if I think it's a less than, then where would my result have to be for me to say, sorry, Subway, you're wrong? Sorry, I said less than, but I did it for the greater than. My bad. Let's ignore what I just said. If my claim is that it's greater than, where would my result have to land for me to reject the null hypothesis? On the right side. And if my claim is that it's less than, where would my result have to land for me to claim that it's to reject the null hypothesis? On the left side. So the Subway example would be here. Do I get a value that's way to the left? If I do, maybe I have enough evidence to start my lawsuit.
Wait, did they win anything in the lawsuit?
I don't really remember, to be honest. It's possible. First of all, I'm not really a big chef and whatnot. I don't cook much. I eat a lot, but I don't cook a lot. When you put bread in an oven, does it shrink? So perhaps the original length was 12 and then they heat it up, and I don't know. I mean, who knows? It can lose enough.
So they didn't think about that scenario.
I don't remember. I just remember hearing about this, but I don't really recall the details of what happened.
But they wanted like.
I don't know.
If they wanted like actual, like, you know, like a foot long. like,
Right, is it a foot long after it's heated or before it's heated, right?
You know,
What?
like it should be like 13.
It should be like 13, yes,
Yeah.
right. So what do we have to compute? Well, we got to compute the p-value, right? We got to compute the p-value. We have to compute the p-value. How do we get the p-value? The calculator. You put everything into your calculator and out pops the answer. However, if I did not have the calculator, I might want to actually compute not my z-score, because we're not dealing with a z hypothesis test when I don't know sigma, but rather I would call it a t-score. So if you know sigma, then you want your z-score. If you don't know sigma, then you want your t-score. Well, what's the formula for z-scores? Your data point minus the mean over the standard deviation, correct? So in both cases, what's my data point? What is my actual value for this, huh? My sample mean. In both cases, what is a noise? In both cases, my sample mean is X bar. In both cases, my sample mean is X bar. Next, minus the mean, the actual mean. Now, I don't know the actual mean. But remember, every time you do a hypothesis test, you're always working under an assumption. Which assumption are you always working on when you do a hypothesis test?
No.
Well, yes, because that's one of our conditions, but more than that. You work under the assumption the null hypothesis is true. Oh, you think it's true? Well, let's see if my result really works with that. If the null hypothesis is true, what's the mean?
The same. Or equal.
but I don't know mu as a theoretical. What does the null hypothesis claim is the mean?
You know,
Mu naught. The null hypothesis is claiming that mu naught is the true value of the mean, and therefore data point minus mean. And then what do I divide by? I divide by my standard deviation. But the standard deviation of what? Of x bar, which we know is. So in the case where I know sigma, it's sigma over the square root of n. In the case where I don't know sigma and I have to approximate it with something, what would I use? Sx over the square root of n. Oh, that should be a t, not a z. So the same general formula for both. One uses sigma because I know sigma, and one uses s because I don't know sigma. Does that make sense? But at the end of the day, we use our calculators. We don't do it by hand. So let's do an example on the calculator. I'm going to make this one up. We'll continue our subway example. In our subway example, what is our assumed mean if the null hypothesis is true? 12, right? Subway's claiming it's 12. Oh, really? Really? You think it's 12? Well, do we know sigma? Huh? If you don't know, then chances are we don't. So we're going to use a t-test. So mu naught is 12. Now, obviously, it makes no sense just practically for our sample mean to be like 4.3. Okay, if you're asking for a foot long and you keep getting 4.3 inches, someone would have noticed a long time ago, right? So chances are, whoever came up with this lawsuit and measured it, chances are the values were pretty close to 12, but not quite there, right? So what's a good X bar to use for this particular example? 11.5. Let's use 11.5. So you took all your samples and you got a sample mean of 11.5. X bar. Your sample means 11.5. Mu naught is 12, X bar is 11.5. What do you have? You're on data. Switch to stats. Remember, we don't have the data here. We have stats. Now, how large is our sample size? How many sandwiches do we sample? 50. Okay, so 50. N equals 50. And what was our sample standard deviation? 0.5? Okay, 0.5. Suppose our sample standard deviation was 0.5. Because we're picking a random number. I mean, we're just making things up here. So what's our p-value?
Oh, it's 5.14882736
E negative 9. When you see E negative 9, what does that tell you? You move the decimal place 9 spaces to the left. That means 0.000000000, and then whatever those numbers were. Essentially, what's our p-value? For all practical purposes, what's our p-value? 0. And as a result, what do we do here? As a result, what's our claim? We reject the null hypothesis and we take subway to court. I wonder if there's an actual subway hypothesis test for 12-inch subs. I wonder if anything pops up. Here we go. This happened in 2015. Subway will now, this is an article that was after the lawsuit. Subway will now measure its bread to ensure footlong sandwiches are actually 12 inches in length. Well, take a look. Nations Restaurant News writes, the issue first came to light in 2013 when an Australian teenager posted an image on Subway Australia's Facebook page of a foot-long sub next to a tape measure that showed the sandwich was actually 11 inches. A class action lawsuit quickly followed and it's taken the chain 2 years to settle the case. This is an actual thing. Now, they don't, in this article, they don't give the actual data. Yeah, they won. Apparently 45 cents per sandwich. It's the way class action lawsuits work, in case you guys just don't know how the world works, is millions of dollars are usually awarded, if not billions, split amongst all the plaintiffs. Now, if you can prove via receipts that you shopped at Subway and you bought 12-inch sandwiches, you ever get these emails or letters? You are entitled to a whatever. In this case, because they won the class action lawsuit, all of that money will be split amongst everyone who can prove that they ordered a foot-long sandwich at Subway between this time and this time. Excuse me?
They fought for 2 quarters.
Per sandwich.
How many sandwiches are you eating at Subway?
You see this? All of them. Okay. So, anywho, we did not finish the chapter today.